Alright, so for the Frobenius method, it's of this form right here, y of x equals x to the r of the sum of a times x to the m, which equals x to the r of a0 plus a1x plus a2x squared, and so on. So it's just like the power series, but it is an extension. So the main difference in the actual form is the r right here, the x of r term. In the power series method, the r can't be negative, but it can be in the Frobenius method. There's lots of applications for the Frobenius method, which is, I think, mainly what you wanted me to talk about. There's three cases. Case one is when there are distinct roots that don't differ by an integer of 1, 2, 3, so on. Case two is when there's a double root, and case three is roots that differ by an integer, 1, 2, 3, and so on. So in the Euler-Cauchy equation, which is right here, you can use cases 1, 2, and 3 without the logarithm. This explains, or you can use the logarithm in other ways, but in the Euler-Cauchy equation, you don't do the logarithm. For the double root case 2, you can solve this equation: x times x minus 1 times y double prime plus 3x minus 1 y prime plus y equals 0. And then you get r squared equals 0, and that indicates that the double root r equals 0, and then you can insert that value into the equation and solve, and you get two solutions. And then for the log term, this uses case 3, x squared minus x times y double prime minus x y prime plus y equals 0 can be solved with this, and once again you get two different solutions. And then it also talked about the hypergeometric equation, which can be solved by the Frobenius method, but this chapter didn't talk much about it, it just mentioned it.